to sum up, we have just proved the existence of an algebraic closure. So we have proved the existence of an algebraic closure K bar. So this K bar was the union of Ki the set of Ki's was a chain, and each Ki was constructed as follows. It is a field where each polynomial with coefficients and Ki minus 1 has a root. And we constructed this Ki by considering a huge polynomial ring of a huge polynomial ring over over Ki minus 1 by a maximal ideal, a suitable maximal ideal. And to construct a maximal ideal, we first have constructed a proper ideal and then have used Zorn's lemma to derive a maximal ideal. A maximal ideal is obtained by Zorn lemma. So this is a very brief summary of the proof. Now, of course, you may ask, is there any uniqueness result for the algebraic closure? Yes, we have such a result, and to prove this, I have to prove another theorem. I think this is theorem 3 of this lecture, right? This is a theorem on extension of homomorphisms. So let me take K in L in M, algebraic extensions, and let me embed K in some algebraic closure. I have fixed an embedding of K into some algebraic closure of K. Well, then any phi from L into omega extends to phi tilde from M to omega. Any homomorphism phi from L to omega extends to a homomorphism phi tilde from M to omega. And the proof is again an application of Zorn's lemma. Apply Zorn to the following set. The following set E, it will consist of pairs n psi such that n is a sub-extension of M. Well, not K, but better write L here. So it is a subextension, and psi extends phi. Okay, so E is non-empty because, for instance, L phi is an E. Then what is the order? Partially ordered by the following relation. So let's say that n psi is less or equal than n prime psi prime if n isn't embedded into n prime and psi prime extends psi. So psi prime extends psi. Now, any chain n alpha psi alpha has an upper bound. The union of n alpha is a field, is a subextension of M. The phi alpha, well, glued together to give a phi, well, defined in the obvious way. So for x in n alpha, phi of x is phi alpha of x, right? So we take n psi as an upper bound for our chain. So our set E has maximal elements. So let n0 psi 0 be one of them. And suppose that n0 is different from M. So n0 is strictly included in M. Well, now it's very easy to get a contradiction. Take x in M, but not in n0. And consider the minimal polynomial of x over n0. Let alpha be a root in omega in the algebraic closure. Then define n0 of x to omega by sending x to alpha and well, psi 0 on n0. So this gives a contradiction with maximality over n0 psi 0. n0 psi 0 is supposed to be maximal extension, but we have found a way to extend it again to n0 of x. So we got a contradiction, so n0 is equal to m. And we can take, well, how was it denoted? It was denoted, I think, by phi tilde equal psi 0. Okay? So corollary of this theorem about extension of homomorphisms, the algebraic closure is unique up to an isomorphism if omega and omega prime are two algebraic closures of K, they are isomorphic over K. Isomorphic as K algebras. Since you have an embedding of K into omega and to omega prime, and then you extend I to a map phi from omega prime to omega. And in fact, since you can do it in the other direction as well, you eventually obtain that such a map must be an isomorphism. Okay, that's all for today.